Gabriela, who's also working on Gnark and Linea. So it's about proving scalar multiplications in SNARKs. So this work is used in the ZK SNARK library that we use, that we built, so Gnark, and in the ZK EVM that we are developing also, Linea. So for today's outline, I'm going to talk about the motivation why we did this and what are the optimizations that we have. So we are calling it the fake GLE, and I will explain why. So elliptic curve cryptography, so it is used in a wide range of applications, like key agreements, signatures, and also in SNARKs. And so it is independent of SNARKs, but when you use it for SNARKs, there are some times where you need to prove the scalar multiplication, not just to compute it, but to prove it in a SNARK. And this is useful, for example, for SNARK recursion, when you want to do proofs of proofs. So this is widely used in so many ZK EVMs today. So it is also useful for account abstraction. So in the next upgrade of Ethereum Vectra, so there is the introduction of account abstraction. That is, you can sign transactions with your, for example, your iPhone. So you need to verify a signature of a specific elliptic curve called the P256, and also in Verketry for stateless Ethereum. So you need to verify some elliptic curve cryptography in a SNARK. So all of these can benefit from what we developed here. So just to fix some notations, so we have an elliptic curve. So this is just some curve. For example, here given some form, so a short range transform. So y squared is equal to x cubed plus ax plus b with some parameters a and b. And the number of points, either it is prime or it is divisible by a prime, but we work on this suburb. And the operations we are interested in on this elliptic curve is the addition of 2 points, the doubling of 2 points, which is like just adding the point to itself. And most importantly, what I'm talking about today is the scalar multiplication, which is the key operation in elliptic curve cryptography. Which is, so if you multiply a scalar n by a point p, it's like you adding the point to itself n times. So just if you want some illustrations, you can do this. You can see this geometrically where the chord and tangent explains the law of addition or doubling if it is a tangent. So I'm not going to talk about this in detail, but for example, if you want to do, so I was talking about proof recursion, so SNARK recursion, so you have a first proof that verifies some statement, and then you want a proof that verifies the other proof. But if the verification of the first proof uses elliptic curve cryptography, you need to be able to prove this efficiently in a SNARK circuit. ZK EVMs, for example, so the signatures today on Ethereum, they use SEC-P256K1 curve. So for a ZK EVM, they need to verify the signatures in a SNARK, wherever the SNARK is. And so there are elliptic curves precompiled. So there is a scalar multiplication on a specific curve called BN254. And soon on a different elliptic curve called BNS2381. For account abstractions, you need to verify the CDSA signatures over the P256 or ED25519 curve. Verketry, you need to do scalar multiplication over different other elliptic curves called Bandersnatch. But the same thing here is you need to do elliptic curve cryptography over these curves. And for example, for Linea, we do the SNARK aggregation with 2 other elliptic curves called BLS12377 and BW7760. So there's like 1, 2, 3, 4, 5, 6, 7 curves, but the problem is the same, doing scalar multiplications in a SNARK. But the question is, can we do this efficiently on all these curves or not? And the answer is not pretty much. So there is the standard scalar multiplication, which is like this double and add algorithm. So your scalar, you just write it in bits, and if the bit is 0, you double. If the bit is 1, you double and add. So this is the most standard way to do scalar multiplication, independently of SNARKs. So if we remember our curves here, so this works for all these curves, right? Because it's the standard way. But if we have what we call the GLE endomorphism, if the elliptic curve has some special structure, we can speed up this algorithm pretty much. And here I'm giving an example. So most of the curves have this this form, so which is y squared equal to x cubed plus b, so the a is equal to 0. So, and this particular form gives rise to an efficient endomorphism. And what I mean here is like, if you have some constant, like I'm calling here lambda, and you do the scalar multiplication of lambda by the point speed, you can substitute this by a very easy computation, which is like the image by the endomorphism. You just multiply the coordinate x by some fixed element, and you give this coordinate y. So whenever you have a multiplication by this big fixed lambda, you can substitute it by something cheaper. So this is an example, and it applies for all the curves I mentioned. So SEC-P256 for ECDSA on Ethereum, BN254 for precompiled, BLS-12381 for the new precompiled in Vectra, and for these two curves for example, for linear aggregation. Another example, which is not widely used, but it is used, for example, for Verkel trees. So Verkel trees, they use this Bandersnatch, and it has also an endomorphism. It's a bit more complicated than the other one, but it can also be useful to speed up the scalar multiplication. And how do we speed up the scalar multiplication? It is well known in the literature. So whenever you need to compute the scalar multiplication of S by the point P, if there is a way to write this scalar S as S1 plus this fixed lambda times S2 modulo the single order R, and you guarantee that S1 and S2 are twice smaller than S, then you can substitute S times P by S1 times P and lambda S2 times P, which is S1 times P plus S2 times phi of P. And phi of P, we said it is cheaper. And why this is cheaper to compute? It's because the key thing is computing S times P with S on n bits is more expensive than computing the sum of S1 and S2 times two other points where S1 and S2 are half the size of S, so n out of 2 bits. And this is what is called symmetry. And the algorithm is just this: you just pre-compute P plus 1, P plus P of P, and then whether your bit is 0 or 1, you do the linear combinations, and it saves you computation. So this is all known in the literature, independently of SNARKs. But if we want to translate this into SNARKs, so we can translate the double and algorithm, the standard one, and it works for all the curves. But if we want to do GLB-like, we can also do it, but it is specific only to the curves that are equipped with this endomorphism. So the SEC-P, the BN, the BLS, but not, for instance, the NIST P256 for account abstraction. And for account abstraction, one way to do this is to do a snark of this ECDSA over P256, and then to verify the proof function. So we have an optimized implementation in Gnark for both of these algorithms. So just to recall, so the standard algorithm works for account abstraction, so for P256 and PD255-19, and the GLB algorithm works pretty much for all the curves we are interested in: SEC-P, BN, BLS, and BW6, and also Bandersnatch. But now the contribution of this talk is basically I will prove that in SNARK, not outside, you can do GLB for every curve. You don't care about if the curve has an efficient endomorphism or not. So the efficient endomorphism morally is just a way to go from S times P with S on n bits to two scalar multiplications, so the addition of two scalar multiplications where the scalars are half the size. So this is by using phi here, which is the efficient endomorphism. But in circuits, we can find a workaround of this without having phi. So instead of computing S times P is equal to Q. So actually, the key thing here is we're proving this scalar multiplication as now. So we know the results already, which is Q. So we can prove that S times P minus Q is equal to 0, to the 0 post. Okay? So if I find a magic scalar V that is not 0, and I multiply it by this equation, so it becomes V times S times P minus V times Q is equal to V times 0, which is just v times s times p minus v times q is equal to 0. But if I find this v in a way that the initial scalar s can be equal to u out of v modulo r, with u and v half the size, so which is like smaller than square root of r, then I transform the scalar multiplication sp to the scalar multiplication up minus vq with u and v twice smaller. So I just found a way to do this without having the efficient endomorphism field. And the question is whether it is possible to do, I'll give you an integer, modulo r, and I ask you if you can write it as a fraction u out of v with u and v small. And here, precisely smaller than square root of r. And the answer is yes, we can do this with, I'm calling the half GCD algorithm, which is just the rational reconstruction. So it's just running the GCD algorithm halfway and stopping halfway. And yeah, you can find this explanation of this algorithm in this hacking. But the answer is yes, you can do it, and you can do it very quickly. So we implemented this. So in circuit, for instance, if you take the scalar multiplication s times p, so in terms of constraints, so here SCS refers to the Planckish constraint. So for example, the old way to do it, so it's 700K constraint in Planckish and 18600K constraint in RLCS. And with this technique that we're calling FAGA, so yeah, we reduced by almost half Planckish and also reduced by 8600 the RLCS. And I'm just giving here for the ECDSA verification, which is like just 2 scalar multiplications. But that doesn't stop here, because the nature of the question then is, we just found a way to do GLB scalar multiplication in circuits without having an efficient endomorphism. So it works for all the curves. But what if the curve has an endomorphism? Can we benefit from both the ordinary GLB and this fake GLB? And the answer is yes. And this is what we call 4D fake GLB, so the 4-dimensional fake GLB, which is, so if you have your subgroup folder R, you can apply the half GCD on R, which is like just writing it as R1 times lambda times R2. With lambda is this fixed element, well, it is the eigenvalue of the endomorphism here. So this we can recompute it. We know R1, we know R2. And then the thing is, so similarly, so before what we did here, we were looking for writing S as U out of V, mod R. Here, we are going to write S as U1 times lambda U2 out of V1 times lambda V2, modulo R1 plus lambda times R2. So we will be applying the half GCD the same way that we did before, but before we applied it to Z, related to Z numbers, but here we're going to apply it to a very specific field, which is K, which is like the algebraic numbers Q lambda out of the variation polynomial. So it depends on the specific elliptic curve, but for example, for all the curves that we are interested in, so they have this, what we call the J invariant 0 endomorphism, and it just means that this field K is the Eisenstein ring of integers. And I'm not gonna go into this in details, but all the examples, basically they have this lambda as a third root of unity modulo R. So it is just the ring of Eisenstein integers. And the example of Bandersnatch, it is slightly different. So lambda is square root of -2 mod R. So it is another ring, but not a known one. So there is like Eisenstein and Euler, but this one is different. But it is also an Euclidean domain. So it means that you can do the GCD then. So yeah, Eisenstein integers are those algebraic integers. So with the omega here, which is our third root of unity. So they are of the form A plus BW. So similar to complex numbers that we all know about, but here it's a bit more complicated because so complex numbers, you have omega squared is equal to -1, here omega squared is equal to minus omega minus 1. But all the laws, we can define them the same way, so the multiplication, the norm, the quotient, so we can implement the half GCD algorithm with the global constant 1 out of 2, which means that every time we do the half GCD at iteration, we divide norm by 2. But the thing is, the norm we are interested in, which defines the number of bits in our for loop, is the infinity norm, but here it's the complex module, which is like a different norm, so in this formula. So when I said here, so finding U1, U2, V1, V2 smaller than R to 1 out of 4, so we divide the size, the bit size by 4, we need to add a constancy. And we prove in the paper that the constant is this one, which means that for 128 bits of security, the for loop we need to add 9 bits. So it's the size divided by 4 plus 9 bits. And we actually implemented this in Gnark, and we use this in Linea. And here I'm giving the example. So here I'm comparing the ordinary GLV with the new 4-dimensional fake GLV. And we see that we reduced by 100K the number of constraints. So for SecP, for BN, for BW6, and for BAS12. And yeah, so that's it for me. But just to recapitulate, so there are 2 contributions. One is we can speed up the proving of the scalar multiplication wherever the curve is, which, for example, question the choice of Bandersnatch over Jug for vertical trees. So the Ethereum Foundation chose Bandersnatch because it has an isomorphism, but here we know that we can have the benefit of isomorphism without having it in circuits. And the other thing is for pre-compiles, for account abstraction, for SNARK recursion, we speed up by a lot the number of constraints. So yeah, people shouldn't be afraid of doing elliptical cryptography in SNARKs. So it is said to be very difficult, but yeah, 200K is not that much in terms of number of constraints. And yeah, that's it from me today, and happy to take any questions.
Thank you. Any questions?
I have a question. So in your scalar multiplication, you do division of bits just once, right? Like you receive 2 scalars, but the size of the half. Can you continue doing this division recursively, like because you're saying that health is faster to calculate?
So yeah, there are 2 things. We do the division, but in circuit we don't do the division, because in circuits what you can do is you do the division outside. So you write S1 as this, S as S1 plus lambda S2, and in circuit you just check that S is equal to S1 plus lambda S2. So this computation is not expensive. And the other question is, can we do this recursively? You can, but it wouldn't change anything, because here, when you do it, so you do it modulo R, so the size is half the size of R. So if you do it again modulo R, the size will be half the size of R. So it's gonna be the same size. So you can do it only once.